And so you can go to Uppsala in 40 minutes by train. 45 minutes is train right. Anyway, so by some coincidence, they were also organizing some climate workshop there. And so these are the days for our final conference. Is the 25th, 26th, and 27th of May that we have put on our announcement. But there's still no detailed schedule of our conference. Now there, staying in Uppsala here, is going on these 2 days, Thursday and Friday, 26th and 27th, but only until lunch on Friday. And when we look at their program, it seems like it could be that the program on Thursday is interesting for people here as well. So I put forward, I just talked to the organizers there. One idea, possible idea, could be that we join forces on Thursday and we take perhaps 3 of the speakers from this program here and put them in the Uppsala program on Thursday. And then all who want, probably many of the people here, will then go to Uppsala and listen and actually spend Thursday in Uppsala. And then we go back here Friday. So the question is how you would react to this. I think we shouldn't discuss this now, we'll discuss this after that seminar. And just move forward this idea. And this is the program here. Friday. So Michael Gill here, for instance, on Friday, he has anyways been scheduled for both events. So he will also these other people are only in Uppsala. And maybe you could put up here the Thursday. Yeah. Could you put up the first Thursday schedule again here? So the people speaking in Uppsala on Thursday are Henk Dijkstra, he's in Paleo Climate, Silvia Del Monte, I don't know her, towards high resolution ecological bioprocesses in the global oceans, well, something with biology, chemistry, perhaps in the global ocean. Chaotic stirring, Francesco Lovidio, also biogeochemical cases here. And then tropical cyclone risk assessment. This is what's scheduled now for Thursday.
And they would agree to take on another 3 talks.
Yeah. They think it's good if they have more audience and if we can bring in 3 more speakers. Okay, so let's discuss that later. And so let me introduce then today's speaker. And most of you have seen him already during last week. Speaker is Serbian. Dobricic. And so Serbian, he took his his basic degree in meteorology in University of Belgrade in '91. And then later he took his PhD in Hamburg, in environmental sciences in 2002. And then now he's working in Bologna. He's been there since 2004, working on data assimilation in an oceanographic model. He's at the center, newly formed Center for
Climate Change.
Mediterranean.
It's Euro-Mediterranean Center for Climate Change.
European.
It's an Italian institution, so it's a first of the kind. So we are kind of consortium between different institutes, where the groups from different institutes have merged to study climate change. To kind of have a center but Italian.
Okay. I could mention also the Jenny Nilsson who just arrived today.
Yes.
He's also at the same institute.
Yes.
So please.
Yes, thank you. So thank you very much. Today I will talk about something that was that I started to work with about 4 years ago, and that has evolved as my research. This I call sequential variational method, and it will be obvious afterwards why I call it like this. And the acronym will be SVAR, so when I mention this SVAR will be something for this. The latest development I have made is to try to apply this without having to use the tangent limit and the giant models. Now my talk will first give just the formulation, a formulation of the weak 40-bar problem. And then I will say something about the motivation for my study. And then I will theoretically decompose this 40-bar equation in a form that may be more simple to solve. And then I will show how it will be possible to approximate the solution of this decomposed system by using tangent linear and joint models. And then I will also show how it could be possible to do the same thing without using tangent linear and joint models. And then I will show also how in this framework you can actually have a very efficient solution, numerical efficient solutions to go backwards, so having observations in the future to estimate what were the previous states, bringing those states that were observed in the future. One part of my talk will be really very accurate, and the second part, the second part will deal with the approximations, with our practical approximations used for the solution of the problem. So here I give a solution, a formulation of the weak 40-bar. So here we have a term which is the background, which estimates the uncertainty now background state at time 0. And then we have at different time steps, can be 1 day or several hours, or well, whatever, we have observations way, and we have the mapping from our states xk to the observations. We also have another term which introduces the uncertainty in the model, so the model error. Here we have that there is a difference between what model estimates as the state at time step k, and that what is consistent in a statistical sense with then observations. So we assume that both the model is imperfect by having an error eta, or difference eta, and also the observations by this mu. An important assumption here is that observational errors, so this mu and eta, also the model errors, are uncorrelated in time. So we assume that there are no biases. Well, it's an important assumption because we actually know that, for example, models have strong biases. But we can also think that if we have many observations, then in short term, if we have a short step between the two observational data sets in time, then the major part of the model error is actually a random error which is not biased in time. The biases arise in longer simulations. So that's an assumption.
Yes, wouldn't it just be easier to augment the model with a bias term that evolved in time?
Yes, that's another possibility, to put a bias term that involves in time, but that this has a single spatial structure. Not a single spatial structure, but the spatial structure doesn't change with time. In that sense, yes. And then it would be simpler to do that. But this is maybe more general, because here we can put different. We assume that the model error can change in time, and this can happen because we can have different dynamical evolvement, and in a non-linear frame especially we would expect that having a different background field we would have different model errors.
But I think the statistician would probably structure this by having the biases held on the spatial basis vector, or collection basis vectors with evolving coefficients.
Okay, yes, that's possible. Yes, that's also. But I think there were some. I think there is at least one paper that does that I know of that uses this form where you have the spatial spectrum. Yes, spatial some spectrum, then you can evolve with time. But that's another solution. Okay, so in order to minimize this efficiently, we can linearize this equation. And the linearization actually says that this difference now becomes simply some delta x, and we also introduce d, which is the difference between the observation and the background term. So the term that is xk given by some first estimate, because here it is not the background, it's the optimal state estimate. And then by the difference here is h is now linearized observational operator. And we have a delta x, which is again the same as here. No, it's different because now this is the estimate that takes into account both the previous observations and the future observations. And we have here eta k is simply the difference between linearized the xk and m times delta xk and m times delta xk minus 1. So that this if we make some perturbations of form of delta x, we can linearize also this equation, and then we can just this term becomes just we can write as eta also, just like here. So now the problem.
Which are the control variables?
Sorry. Yes.
The control variable.
The control variable is delta x over all time steps. So starting from k equal to 0 to n.
You can add eta k as the control variable.
You can also add eta k because there is a dependence between them, a linear relationship. So it can be either eta k, but I use delta x as the control variable. Always think as delta x.
I mean, when you say delta x, including delta x hat.
Yes.
The one in the second term.
Yes. Yes. This is the control variable, but also this one. Why did I put here tilde exactly now? Because it's okay. Because I wanted to say actually that here, as I will show later, actually the background state you can define different ways. So here it's just given by something. I have some estimate of the background field, but here I can say that in my application, I have a freedom to define differently the background state. So I don't use this tilde, but I use a hat just to say that there is a freedom to define instead of having like tilde is given. So I cannot change it. It's something that is the initial state I have. But this one I can define in different ways. I'll show later.
Have you in mind an idea of iterative processes with inner loops and outer loops? Like is then, so that
yes,
the delta x hat will be
yes,
a deviation to some
yes,
current estimate.
yes, exactly. It can change. It can change by.
And then you start a new basic solution.
Yes, if you have a non-linear trajectory, you can adjust the trajectory,
yes,
so it can change.
Yes, problem in the vicinity of each linear estimate.
Yes, yes. Yes, yes, and then the delta x becomes different in every iteration. But there is a little bit more of that. I'll show later. Maybe.
What is dk? As I know it's related to yk, but is it
dk
yk minus?
Yk is h times xk background. So having you must have some background value. So it's a misfit or residual.
So dk is the observation residual.
Yes.
It's the innovation.
Innovations. So, so here we have a big problem that arises here. That at least to me it seemed that at the beginning is that actually if you don't have this term here, so if you assume that the model is perfect, all what we have to do is to minimize the initial condition. That is so that the model space. Has the dimension of the model itself. So the number of model points times the number of parameters we want to use in the minimization. If we have a weak formulation, this grows as with n. This is proportional to n. So if we want to do, for example, 1 year of reanalysis, this becomes 365 times bigger. So it can grow very much as in this. So this was my first motivation, was to study how to do this in a way to minimize minimize the use of the space on the computer. So to fit this more easily to some realistic computer. So then another thing that arose in this work when I started to work was that actually what comes out that 40 bar gives an optimal estimate of the mean state or the most likelihood state, but doesn't give the background error covariances at the end of the assimilation window. You can calculate them at the beginning, but not at the end. And
so what do you mean by the background error covariances here?
that's the matrix of that is the second moment. So we have the first moment, but not the second moment.
So that's not quite true, is it? Because if you think about the 4D bar within a Bayesian framework, then the curvature of the loss function would be a reasonable approximation to the inverse of the
at your
variance.
state at the beginning, not at the end.
Well, no, but your loss function is defined over the entire collection of innovations, isn't it?
Yes.
It's a very big calculation to do, I agree.
Yes.
But
That's right.
you know,
Yes,
in
yes,
principle
that's
you could
true. Yes,
extract.
that's in fact that's true. Yes, yes, that's true.
In principle.
Yes. Well, anyway, it is not. There are some methods that especially I saw in, as you say, it's very computationally demanding, and in representative method there are some proposals, but again it's hard to achieve that computation. So, in comparison to the extended Kalman filter, it was not something that I really had motivated, but going through the steps of this work, I came to also this thing that it comes out that in extended Kalman filter it seems to have more ability to treat non-linearities in the model. So I will explain this later why this will be why this I think happens. And then the latest thing that was my motivation to further work on this was that actually a big technical complication, especially if you have complicated ocean and atmospheric models, is that you have to develop tangent linear and also its joint. So it's possible, you can do this, but this takes lots of time and it's quite hard. I did it several, so I think I wouldn't like to repeat this job every while. I mean, this was it's a very, how to say, very hard job and takes lots of time. Requires also the scientific and technical knowledge, so in programming.
Were you using software to automatically differentiate those?
You can actually, no, that's possible, but still you have to be careful when you use that. And you have to control.
That work.
Yes, I did everything with the software and then I would control, but still doing all of this is a very long process and you have to be very careful. And I mean, it's not a scientific job to do, but it requires both, I think, scientific and understanding what you do, actually. You must try to understand what you do. So this is just to say something about the dimension of the space. So we want to do, one of the things that we want to do are the reanalysis. So we want to have a long time reanalysis. Let's say the ideal would be for the last 4 or 5 decades. And we have a quite large model state size for 1 day reanalysis. It's about 10 to the 8th. And then for a 5 years long period, this becomes about 10 to the 11. So the size of the space on which we would define this weak 40 bar cost function. So this is large space. So I was trying to think about how to practically solve the problem over this large space. So I looked at a single time step. So just what happens when we suppose that we know what are the background error covariances at time step k minus 1, and we just have 2 time steps, k minus 1 and k. So what we can do here is that we can make a partial derivative with respect to delta x k minus 1 by keeping eta fixed here, and then we get this form. So this one is simply 0 because it's fixed. And similarly, if we make the partial derivative with respect to eta k, this one is fixed and it's 0, and then we have this one. So we can now rearrange these two gradients of the same cost function. These are the gradients in different directions, in the direction of xk minus 1 and eta k. And actually by multiplying one by nbk minus 1 and the other one by qk, we can rearrange these two. We get this equation, which we can multiply by this matrix on minus 1. And we get this gradient. So here, this is not any more equivalent to this, but it just follows from this because there were two equations and we came to a single gradient. From two gradients, we tried to form a single gradient. Now this gradient is actually different because it is only over delta xk. And we can see that this is actually a gradient, or also a gradient of this cost function. So this cost function, if we manage to minimize this cost function, actually we will get the same solution, delta x k, as we would achieve by minimizing the cost function that we had at the beginning, this one, which had xk minus 1 and eta k. So the advantage possible here is that actually we have the model space which was defined over two time steps, over this time step k minus 1 and k, but now we arrive to the solution over a single time step, only time step k. A disadvantage is that there appears this matrix, which is now very complicated to estimate. This is, instead of having before, we could, if we knew this matrix and this one, then it's quite straightforward to solve this. But here we have a matrix which involves, it has an inversion of a matrix where we have the model operator inside. So this is a very complicated term to estimate, a matrix to apply directly. So now we would also like to have the estimate at time k minus 1. So we can again look at our initial cost function, which is this one. Here I just, instead of eta, I wrote the definition of eta through the linearized space, in the linearized equation. And then we look for the minimum of our delta x k minus 1, but now we know this delta x k. So in this case, the second term, this one here, because we know it, is irrelevant, is a constant. So it's irrelevant for the minimization of this cost function. So if we know x times that k, we can recover x at k minus 1 by simply minimizing this cost function. We don't need the whole cost function. So in this case, again, we have, this is known now. We just have to minimize a cost function over the model space defined at a single time step. So we can do sequentially. We can first go forward in time and then go backward in time, but every time applying cost functions. Again, here there is a problem, technical problem, because there remains the operator n. Of course, this can be, it's straightforward to minimize this cost function by well-known methods for minimization using tangent linear joint codes. But actually this requires, again, a minimization that requires many iterations by these models, so it's costly computationally. Because we add computational cost, we have to first use lots of computational cost to go forward in time, and then we have to do it, so we approximately double the computational cost in this case. Okay, so how to estimate now this matrix? This is the central problem, I think, in the whole of this algorithm when we move to it. So actually this one is supposedly, we suppose that we know what the model errors look like, or we can somehow guess that. But the problem is how to evolve this matrix Vk minus 1 by the model operator. So we can do it directly multiplying, which is the original formulation, for example, in Kalman filter. So we just apply the model operator to the matrix. Or we can use ensemble methods, yes, which is or we can even, I've never seen this, but for example, we can use sequential Monte Carlo methods, which would then generate an estimate of this matrix. In principle, it's possible. Here, what I wanted to do is actually use. Originally, they were. Later, I just stopped to this Lanczos method, but to use well-known variational algorithms to implicitly actually estimate this matrix. So instead of doing this implicitly, so when we minimize the cost function, we also need to know actually how is this curvature looking like. So we use either Lanczos or BFGS, so-called method, to estimate the second derivative of the cost function, which is actually this comes to this form of a matrix, and in an efficient computational way. Yes.
So usually you would never compute that outer product.
No, in fact,
because
yes.
the result would not be positive, definite, symmetric by construction. So usually you wouldn't hold B, big B at all. You would hold for example, the Cholesky decomposition of
that's
B.
right. Yes. That's how I'm going to do that later. Yes. Exactly. Yes. Thank you. Okay. So the idea is here to stay on this variational framework and to try to estimate this matrix by a method which is. These are methods well known in linear algebra to estimate actually these matrices. So we may instead, we can just form another cost function, which I call n here, and make some perturbations. Where these perturbations are, but we can define them as we like. There are some perturbations around some state xk, which is our background state at time step k. Because we know what is the minimum. The minimum of this cost function is simply delta p equals 0, but we can ignore it and, for example, iteratively using the BFGS algorithm, estimate this matrix. Or we can simply apply iteratively the Lanczos method by iterating, multiplying from the right-hand side by first randomly chosen vector and then by estimates of further subspaces, this matrix, and estimate the major singular values or eigenvalues of this symmetric matrix with the corresponding eigenvectors. Actually, the whole problem here is to estimate this matrix. So we can write it in this form, the perturbations, let's say this cost function, or we can rewrite it in this form, where delta p star is the adjoint variable at time step k minus 1. So if it's a very interesting, I think, way to look at this equation, which appears in all Kalman filter formulations, is that delta p is actually a perturbation at the time step k, but as we can see by a joint model integration, we have a perturbation which is the adjoint perturbation which corresponds at the time step k minus 1, which corresponds to this perturbation. So that the possible solutions at the time step k, they are through the adjoint model, they are linked to the solutions at the time step k minus 1, and in a way that they must be consistent with the background error covariances at time step k minus 1. So I think this is just a different view of this what the Kalman filter actually does with this equation. So it propagates in time perturbations, but it also limits somehow the solution to that adjoint subspace which is defined at the k minus 1. Okay, so this is now straightforward to estimate. If you know this, we can simply make perturbations, apply the adjoint model backwards in time. weight these perturbations, adjoint perturbations at time k minus 1 by background error covariances at time k minus 1, and then propagate them forward in time by the tangent linear model to form to estimate the perturbation. So we can actually, technically, this is straightforward to solve. It's exactly the same as what we would do for any cost function, how to solve it. So we can generate a set of consecutive solutions, vectors that would define our, now, okay, let me just pick this. Okay, this I can also skip. This is not really important, I think. This is well known. I will tell later. So, if you use the Lanczos algorithm, which is particularly efficient, so if this is j second, is the second derivative of our cost function, actually, by Lanczos algorithm, we iteratively form a three-diagonal matrix T, and the matrix Q that has forms an orthonormal basis for the Krylov subspaces. And these matrices T and Q, they form, they are, and J secundum are related in this form. So the multiplication of J secundum by Q will give T, or if you don't do this estimate for a long time, so we will have actually, we can also estimate J secundum as approximately as, if we multiply from the left by Q, we will get QT, Q transpose, plus some remaining part. But a big advantage of the Lanczos method is that in each iteration of the algorithm, the previous subspace, Krylov subspace, the new Krylov this Lanczos vector is orthogonal to all previous Lanczos vectors. And in addition, it has the largest norm of all remaining Lanczos vectors. So we are doing, in a way, implicitly an eigenvalue decomposition of the symmetric matrix G secundum. So we know that even if you do partial eigenvector decomposition, this decomposition is somehow optimal in the sense that we manage to most accurately approximate this matrix if we consider the magnitude of its eigenvalues. So this is, for example, this is a big difference between this and ensemble methods in a way that it is not stochastic. It's deterministic and it searches. It's like a conjugate gradient method that searches always in orthogonal directions and tries and looks in these directions that are minimizing the most, going most over the solution, so having the most accurate solution.
Just to check, so J is always symmetric by construction, but it's only
Yes.
positive definite at the solution.
Sorry?
It's only positive definite if you're maximizing or
Yes.
minimizing at the solution, isn't it? It's not positive definite everywhere. So
No, it's true. Yes,
this
but this is quite. There is RPAC package which is quite stable, so you can use it even if it is not exactly.
okay.
So it converges very quickly. Actually.
Right.
So RPAC package is a Fortran and C package that is also in MATLAB, but you cannot use it with models, only with matrices. So which has an implementation of this method, which is very efficient computationally. So, okay, I will just now reassume what is this method looking like. So we have for some k going from 1 to n, we get our background estimate starting from some previous estimate of x of x, and then we estimate also by this, for example, Lanczos method, the evolution of background error covariances, that is this matrix. And then we use this matrix, which is now expressed, because I didn't say, I'm sorry. Now, once you estimate your matrices T and Q, it's very easy to make the eigenvalue decomposition, because this only this T contains eigenvalues, and this is a three-diagonal matrix, so it's very straightforward to estimate the eigenvalues and eigenvectors. So we can this matrix we now estimate as an eigenvalue decomposition, so we can either use the control variable transformation, which is usually used, or we can even directly invert this matrix. But I practically use the control variable transformation, and this is actually a 3D var equation in which we have a background error covariances that now evolve with the equations of the model. And then we have to update the background error covariances, so we can form another cost function in which we perturb all the model space in a way to, again, using the Lanczos method, we can estimate the update of the background error covariances. So we have another step. So these two equations are actually well known, and this is a 3D var, and this is the estimate that was done, I think, at ECMWF. I know they have, in the 90s, they were using this method to estimate the second derivative already for background error covariances, for estimating what would be the uncertainty in the analysis. And finally, we can simply update our estimate by this correction, or this that comes from the observations in time step k. This update now is only valid for observations that are up to that time step, so it doesn't take into account the future observations. Now to get into account the future observations, once we come to the time step n, we have to go backwards, and then we apply this cost function, which is again a function defined only over delta xk minus 1. So we have a straightforward way to go backwards and to solve it. So if you compare this to the Kalman-Smuter equations, which are actually the original formulation of the Kalman-Smuter, but there is a paper by Bell in 1990 something. It's dealing with the extended Kalman-Smuter, so with a non-linear model. So we get these are the equations. So we have that again. We propagate forward in time the state from k minus 1 to k. We estimate directly the background error covariances. We then update. This is our k, the Kalman gain matrix, and then we estimate what is the. And then we can go backward by this equation. So actually we can see that every of these equations that are now formulated in a variational form has its actually analog in Kalman-Smuter equations. And actually this can be directly shown that by taking the gradient from these equations and then rearranging terms, actually we can get the same this set of equations. So this can be strictly proven, but here is just to show that actually the procedure is exactly the same. Yes. So this is why I think that Kalman-Smuter can treat better nonlinear problems. So in practice, actually, it's not by that Ford var has this problem, but it's in practice. In practice, what we do in Ford var, we must first run over the whole window one simulation, which is our background trajectory, and then we linearize around this trajectory. Now, this is not necessary, as Olivier has shown last time, but there is a solution in which you can gradually extend your integration, your simulation window, and that solves this problem, but it is solved as an extra computational cost. So you have, I guess, n½ approximately more computations to do. Time steps. So it's times. So it extends so it's difficult to apply it in a big problem. And so what happens? Well, of course, initially you can have a small error, and you can easily minimize, because one of the assumptions when you minimize is that this delta x should be small, because you have a nonlinear process and you cannot go away too much from that nonlinear process. So you have to be close to the observation so that your corrections are small. But as the window becomes longer and longer, this is not anymore the case, as you can imagine. Because here we don't correct anything by observations. But in a Kalman-Smuter filter, every time step we do adjust our trajectory closer to the observation. So we always remain, because we always have to do shorter integrations, we always remain close in our prediction to the observation, or at least we hope so. But in general, this can happen that by doing the long integration, you are far away from your observation, when here you're close. And one of the problems is that if your non-linear function is strongly non-linear, it's more probable that you will have a false minima between here than between here. So the possibility of having more minima than you will have is also defined not only by the non-linearity of the process, but of how good is your first guess, your background state. So this is why I think, of course, there are now some methods I've heard that at least in the LBF they try to do the 3D bar first, and then to construct a trajectory around which they would minimize. So that's a way to do it in a way. But this is, in Kalman filter, it's more straightforward to get that. So the highest computational cost, okay, now I'll say, this was more, let's say, theoretical background, but now I'll say a few words about how this can be done in practice by not doing too many integrations by the model, because that's what I want to achieve, to make as small as possible the number of iterations of the model, integrations by the model. So this is the equation, this is the matrix I want to estimate. Actually that one has the highest computational cost. So what I propose here is to divide this matrix into two terms. One is the evolved term, and the other one is the steady term. So that I say that just as I do in when I linearize the model, I have two terms. So this evolved term is simply the difference between the two terms. But now my hypothesis or assumption is that this matrix can be represented by a smaller number of eigenvectors and eigenvalues than this one. So this is maybe the whole, what I can hold in my memory of the computer, or what I can represent. And this is something that I want to estimate by integrating the model. So this is quite straightforward in this form. So I can sorry, this is okay, then I can just say. So I apply, actually, this is also a symmetric matrix, and it is not necessarily positively defined, but it's still a real matrix. So its eigenvalues are real values, and so it's easy to get that solution. So this can be solved now by the Lanczos method, using the tangent linear and the joint models. But what came, my last work was, and this all up to this, oh no, maybe I'm just, it's already a paper that I have submitted a few months ago to Manfred and the review. So also this previous slide. But also this one is that actually it's not necessary to use the adjoint and tangent linear models to estimate the matrix of this form. So again, we would like to divide the matrix into two terms. This one is the previous, and this is the difference from the previous. So again, we apply the same assumption that the difference between the two background error covariances can be represented by a smaller number of these Krylov subspaces. And I can apply a simple Newtonian formulation of the linearized model. So simply that but always I need, of course, that I multiply it by vector s. So I can say that it's simply approximately the non-linear integration of the perturbed initial state minus the non-linear integration of unperturbed state. And then I can rewrite this equation in where I decompose this inner matrix. Now I can do, as you mentioned, I could do any kind of square root decomposition. Here I choose to do eigenvalue decomposition, simply again by the Lanczos method. In this case I can write it in this way. So I have actually the same matrix. So this is well known altogether because it's exactly what is used, for example, in ensemble methods. Or sorry. Lost. No, okay, here it is. Okay, and then I propose now to use the Arnoldi method. Arnoldi is actually an extension of the Lanchos method, and it's again related to this estimating in the so estimating these subspaces that are always orthogonal to each other, and then try to estimate the major eigenvalues of a matrix. Well, the extension is that now the matrix does not have to be symmetric. So that's very important, because in the previous case we can see that we have a multiplication of two matrices, and that so if we are able to estimate this matrix here, actually it's sufficient to multiply by its transpose to estimate the full matrix. So we could use this Arnoldi method actually to estimate this matrix, and then by multiplying by its transpose we can get to the full matrix. But in that case we only have to multiply by the forward model, and this forward model, linearized model, can be approximated by this equation. So we are not anymore limited by necessity to develop tangent linear and adjoint codes, because tangent linear is actually not necessary. You can always approximate it fairly accurately by this equation, but it's necessary to build the adjoint model. You cannot build a joint model for this equation.
But that's only true as small as
yes, that's right, exactly. But also our linearization is actually true only for small terms. So of course, yes, that's right. That's exactly. This is an approximation, of course. This is not a true solution. Okay, so what does it this? It has a very similar. So we make another matrix which I call here H, which is not an observation operator, but it's some HS, which is an upper Hessenberg matrix, which is actually a upper triangular matrix almost. It has also one line, diagonal line below the main diagonal, and all other, and the rest below is 0. So this matrix is very easy. It's small also because it's defined only above this subspace, not over the whole space. And then we have these so-called Ritz vectors that multiply our matrix C, which is this non-symmetric matrix. We still require that the matrix is a square matrix, and this is not really the case here. So here we can see that our matrix here is not square, because here the dimension is a model space dimension times the number of eigenvectors that we have in it. So this is a non-symmetric matrix. But still, at least if we manage to have a symmetric matrix, we can estimate its major eigenvalues and eigenvectors through this decomposition. And this one can, so what comes out is that this one contains actually the eigenvalues of this matrix are also the eigenvalues, major eigenvalues of the matrix C. And furthermore, this S is again orthonormal matrix, so it's an orthonormal projection. And so we again have the only complication is actually that this is not anymore tridiagonal, but it has a small size and it's very easy to estimate the eigenvalues that we want. But actually we will never do that, because in this case we are not interested in going to the eigenvalues. Here also the problem is that having a non-symmetric matrix, the eigenvalues are not always real numbers, so they can become complex numbers. And complex numbers then can all become much more complicated. But these are all real matrices. So we don't have to go to the eigenvalue decomposition, but only to this step of estimating the upper Hessenberg matrix and the Ritz vectors. There is no proof that this converges really to that. For Lanchos method there is a proof, but there are many applications in engineering, and so they all show that actually this probably happens. So that these methods are able to, these Bernoulli method is able to estimate quite fairly accurately, not perfectly, the major eigenvalues of the matrix. Okay, so what I do, again I want to form this difference, but now I form the difference only on the square root of this matrix, of that previous matrix BKE evolved part. But then I have also to multiply by this V transpose here to make it square, because to be able to do this I must have a square matrix. So to make it square I multiply here. So I have this kind of decomposition. Here sigma is now upper Kassenberg matrix. It's not an eigen. So this is not a diagonal matrix anymore with eigenvalues. But here plus is actually the generalized inverse of this Ritz vectors matrix. Because this would be very inconvenient to have it like this. So I multiply everything from the right by S transpose. So to remove this term here, this generalized inverse here, and then I get that multiplication, that this matrix can be decomposed into this form. Now what is important here to note is that all these vectors are unitary and they are orthogonal, so they're actually projections. So they are not doing, they are not changing the eigenvalues of the solution. They're just projecting, actually here, they project from the full model space to the space defined only by these Ritz vectors, so only by changes in the evolution of background error covariances. And this one projects from the full model space to the space defined only by the eigenvalues and eigenvectors at the time step k minus 1. So they're just limiting the solution to a certain subspace, but they are not changing the solution.
Just to be clear, does S have special properties? Because usually, if S plus was a generalized inverse, then,
yes,
then S plus S trans would not equal S trans.
So here,
yeah, I mean you'd expect S plus to equal S.
I. And then you get only S transpose, because I need to make it square matrix. I wouldn't need this maybe, but it's convenient.
That's not a rule that is a standard property of generalized.
Yes, but actually it is in this case. I mean, S plus times S is I. Define I on the subspace defined by S, not on the full model space.
Okay.
So it's not, yes, that is not I on the model space. So, but anyway, they shouldn't differ in solution. Now,
it's basically it's a projection.
It's a projection, actually. Actually, it's a projection on this Ritz subspace or that we have inside. So it's to do this, well, to make the full, to estimate the full evolution of background error covariances, we have to form also the projection of the bk minus 1. So this is now decomposed into eigenvectors transpose times eigenvalues times eigenvectors. But now I just multiply from the right with this term, just to project everything on the same subspace as I did before. And I get this form. Again, I apply the Arnoldi method. But this is computationally cheap, because it's just multiplying vectors with matrices. So it's just Lapak or Limpak, not Lapak and Blas subroutines calling here. And here it is not cheap, because we have to apply the model. So it has the high computational cost here. Okay, but this can be done in, let's say, only a few iterations, so maybe tens or 100 iterations. So we can estimate tens or 100 of eigenvalues. So now this is a bit complicated, but then what comes out is that I can approximate this term by combining different of these and then putting the transpose, but then in the end it comes that by simply multiplying these sums of these matrices, I can estimate the evolution of the background error covariances. So this is now, I've made a mistake here, I'm sorry. here is missing minus vk minus 1 lambda k minus 1. So there should be in between. So it's only the evolved part. So that now to this. No, I'm sorry. Okay. Okay, this is actually our background error covariance is now projected on this subspace of S delta. So it's not the background error covariance as we want it, but only the part that can be projected of this subspace that changed. And now we have to add the part from that subspace to make that to subtract this in the same subspace. We subtract the full matrix at the k minus 1, and then this what remains is this bka. So we can estimate the evolution of this bkf, which is on the full space, by this part, which is all defined on the subspace of changes, and the previous bk minus 1. So we it's a bit lots of writing, and also coding is not so easy. I mean, it's lots to write, lots of subroutines, but it's actually straightforward. It's just a matrix algebra to do. Okay, so and this is the solution given this without any integration by the tangent linear joint. So you can do this only by so the idea here is to do, for example, if I approximate this one with let's say hundreds of eigenvectors, I can do this here. Here I perform only tens of model integrations and approximate this only by tens of eigenvectors. And then sum together to get, again, a full eigenvector decomposition with hundreds of eigenvectors. Okay, now I don't know if I have some time. Now it's 11:30. I started 10 minutes late. Do you think I can continue? Yes, 10 minutes. I'll try to do it very quickly. This last part. Okay, so this is another thing that I had to solve was this large computational cost of backward terms, where again, as I mentioned before, you still have to use the tangent linear and the joint to minimize this cost function. And the Kalman-Smuter gives a very nice solution, which is just straightforward. Still, it has this problem here. So if you assume now that the Q, your model is almost perfect, so that Q is small, this will be neglected. And here we will have a -1, some terms will cancel, but what we will have actually here is an inversion of the model. So this equation is actually computationally unstable when your model is almost correct. So this Q term is small, this equation becomes unstable. This is a well-known problem, and it's already in the 70s. It was noticed. But on the other hand, this one is computationally stable. So it has a property that is computationally stable, but it's because it doesn't require an inversion of the model. It's a least square solution, which just minimizes the cost function. But what we can do actually is, when we start from this equation, we can do what we usually do in the methodology, is do the control variable transformation. So we go into the space which is defined by this B, where so we define a new control variable in this way, where this Z is defined as a square root of B. So this is not a unique definition, but we can always do it, especially if we have this B as an eigenvalue decomposition, so it's straightforward to make this. So we can rewrite this equation in the following way. And we can see that there is a matrix GK that is NK times ZK that appears. But then this GK now is actually the square root of BKF, the matrix that we did compute in the forward steps. So it is sufficient to save our matrix BK1 minus 1 and BKF, and we don't have to recompute them, because here it would be useless to redo it once again, because it will be just the recomputation of the same matrices. So actually, if you write this problem now in this way, we can minimize this cost function, having this GK saved from the forward steps of the algorithm, and then having this ZK solved from the previous step, knowing this ZK minus 1, we could reconstruct our delta. So it is not necessary to integrate backwards the model. Still the problem here is that if this QK is small, this is unstable. So we can do another transformation again, and rewrite this cost function. Instead of solving one, we can do it 2 times, where we assume that this one is not small anyway. So we would have, first we calculate this pk, and then we calculate zk minus 1, and from zk minus 1 we get delta x. But it's actually possible to solve this also for a very small cube, and it's numerically stable by dividing this into 2 smaller cost functions. But that's all very technical. Now I'll skip this. Okay, even when the model is perfect, we can do this. So then the equation becomes slightly different, but only it's sufficient to minimize only one equation. Assuming that the model is perfect, we can reconstruct the delta x k minus 1 iteratively. Okay, so I made an experiment. So it's a full primitive equations oceanographic model. I have coarse resolution, which is a quarter of a degree. So it's a much smaller, and 3 mouse window. So it's much smaller space, and that's simply because this is not so easy to. Well, it's not too difficult, but it takes time to code all of this, and then if I would have to run it in MPI, it would be very difficult. So I did it without MPI. And so this is not true. This is 3 months along the simulation window. So it can be any length. I just did 3 months because to limit somehow the time, but I'm sure this can run for 10 years without any problems. So this is, for example, the evolution of background error covariances for temperature at 50 meters. And you can see this is some initial estimate, which is our 3D bar estimate, B0. And this is how it evolves after 3 months. So just to show that it somehow works. These are the covariances of temperature from point positioned here. And after 3 months, that has a bit different structure. So probably there is some also advection error. The big problem here in this my experiment was how to specify matrix Q, the model error, and I did it just as a fraction of B0, and it's not very good. But I think that that doesn't. It's just to show that how this can be implemented. So this is, for example, how the trace of BK changes. So we have the trace of the background error covariances. So it's actually quite stable. So when we have growth, the observations actually put it down, and then it can grow. So it has some oscillations in time, which is interesting. This is the trace. No, this is not the trace of BK. These are singular values of the BK matrix in time. So this is time 0 till the end time. So what happens, I'm not sure is it correct or not, but what happens is that there is a shrink of the spectrum of the matrix. So the smaller become, they become smaller, and the larger actually grow, but not significantly. After some, very quickly, there is a quite steady state. So not very steady, but there is an oscillation around some steady state. That's interesting. So this is at a certain time, I think at the end. Okay, this is initial singular vectors, and these are the singular vectors at the end. So you can see that they drop down, but here they have grown a bit. So, but it's important to notice that the eigenvectors here are not corresponding. These eigenvalues do not correspond to the same eigenvectors. So that the subspace in which I define this initially, V0, is different than this subspace, because this is that one that evolves in this. So I have no assumption about the subspace in which I have to have it. It's all done by the algorithm. And this is just to show that the backward integration is computationally stable. This is the maximum kinetic energy of surface velocity, which is the largest velocity in ocean models. And you can see that it's always limited by a very physically reasonable number. And it's just because we have this, cost function formulation of backward steps. So that guarantees us the numerical stability of the solution. But if I compare this to the 3D VAR, this is with looking at misfits or residuals in in the forward sweep of this scheme, with what I get with the 3D var, which is much simpler, it has a number of assumptions, where especially that one about some kind of climatological estimate of background error covariances, I don't gain anything. So actually, this is as accurate as the 3D var. So I'm not sure what is the reason for this result, because here there can be there is no tuning. So this 3D var is very much tuned. So it's our operational scheme, and we have spent years to get it to work very well. And actually, these values are very low. So usually other systems have a lot higher values for this and other parameters. So we are quite how to say, proud of how good we have our system, even compared to the ensemble common filters and so on. So there is still something to work on in this. Now, how this can be related to predictability, I thought, because we are talking about predictability. So I think, in short term, of course, we know that the predictability depends strongly on the initial conditions. So if we have also the probability distribution of some assumption, Gaussian assumption about this initial state distribution, then may help a lot. So we can easily construct an ensemble for the forecast. Another thing that is that we can always, even if we have a very complicated PDF of a certain process, we can approximate it by as a sum of Gaussians. So this can be, for example, taught as something. I think it's something that was mentioned for this in WF. They have an ensemble of 4D vars, but so there could be something similar. But here you also get the background error covariances, so you don't get only the values of the most likelihood state, but you also have the distributions of how probable that state is. And now, how is this related to other common filter schemes? This is also interesting, I think. So, I think it's most similar to SEEK and ESSE scheme. So let's try. So these are the schemes that are actually using the space reduction approach. But actually, they are generally similar to all common filter schemes because they use these equations that have their analogs in common filter. The major difference is here that we don't assume in advance what is our subspace, like in SEEK or this ECS and ESSE. And or in a stochastic way, like in ensemble methods. And there are some methods I saw in engineering later after I finished all of this, and it's a completely different field of literature and people working, and they actually do some reduced order modeling using data. But actually the difference, I think, is that here the reduced order space is used only in estimating the second derivative, not in all the solution. Okay, so I think I'm over. I think that this would be more or less the repetition of what I would have said.
Can you back to slide number 16?
16, yes.
So here you have an iteration from k equals 1 to n, and then a backward iteration from k equals to 1. This would have to be repeated.
Yes. That can be. But here it's. So maybe, but in this case, there is not this problem of minimizing. Actually, by assimilating data in intermediate steps, we may expect, at least hope, that we already have a quite good background estimate because we integrate only one shorter. So we could either integrate only this one, repeat, or we can repeat the whole system. So I don't know, I've never thought about how to do it because I stopped only in one iteration.
Only one iteration of these two, one forward followed by one backward.
One forward for all, just like common filter, and then one backward like common smoother.
Okay.
That's how I work.
First of all, it has to be iterated.
Yes, it would be more accurate by.
So really propagate the information all along content in the observations, all along the assimilation window.
Yes, definitely. In that case, yes. If you want really to have this consistent solution, this will not be stable or accurate unless you iterate.
And then can you go a few slides forward?
Forward,
I
yes.
think number 20.
Yes.
Okay. Stop here. Okay. No, okay. Yeah. So you have BKF equals, and you have an adjoint model at the end, and you make it, and transpose one energy. So
Yes.
here, you do some, which in order to compute this BKF, you use
Yes.
the algorithm and things, which I don't know, but you have to do a space reduction there.
That's right.
You
But this
limit,
is,
you limit some kind, you use the square of spaces.
yes, but it's
you
quite
do a
accurate.
special
Yes, it's quite
Okay,
accurate.
okay.
So you can really see. So what I can do actually, I can reconstruct later. I can do this and then reconstruct my background error covariances, and then see if these are really consistent with what I would get by modeling them, like in the 3D wire, because that's.
So you avoid developing an really energetic model at the price of a space prediction.
V0 doesn't have to, because this is
You
only
do
necessary.
that is it true to say
Yes.
that you do the computation in this space, but it's sufficiently small that you don't need.
That's right. That's right. No,
Okay.
this is exactly. This is an approximation to the full solution which you would get by tangent linear and joint codes. But this is an approximated solution which is for practical reasons. But still, it's not a stochastic solution. It's not like ensemble method, but it's a deterministic. So I have a criterion that says, okay, these major eigenvalues are the best approximation of my matrix. And using this criterion, I can I try to approximate as closely as possible, having a possibility to run a limited number of model integrations. So in ensemble, it's either stochastic or it's somehow defined. I mean, people just do it arbitrarily. They decide what to perturb and how. But here I don't have to decide
And
in advance.
one question.
Yes.
From what I understand, the assumption that errors are uncorrelated in time is critical for you.
Yes, it's important assumption. But that assumption, as I say, in practice could be less important if we have dense in time observational networks. So we may have, for example, if you have lots of observations, which is not really the case in the ocean, especially before the satellite era, but if you have frequent observations, then we can hope that in short term the model error will not be the systematic part of the error, but it will be more random, and then slowly by time it will drift from the, and then the systematic error will overcome.
Yeah, well, correlation in model error manifests itself in other form, but to just
Yes, all filters
bias,
actually assume this.
systematic bias.
All common filters are doing this assumption.
But okay,
Actually, it comes.
it's important that the hypothesis.
Yes, I fully agree.
Of course,
I mean, it's
this hypothesis can always be resolved by just augmenting the state vector x to the time dimension. But
Yes,
but
yes,
the
yes,
coefficient
yes,
of the
exactly, yes.
maybe absolutely.
Yes, because this idea, it's just a technical, it can be applied, but then to the large state vector, but then it becomes practically very difficult to solve it. I fully agree with this.
Hey, can I just come back to the point you raised initially about the... So in a standard Campbell filter with a linear propagation equation, you would go through on the filtering step and then you would go back on the smoothing step, and that would be the end of the whole algorithm. Now you're saying you need to iterate this process. Is that...
My understanding is that, yes, so that was my question. Is it necessary to iterate this?
So my understanding is the iteration a way of undoing some of the damage of the linearization? Is that the purpose of going backwards and forwards?
Well, I think the problem is not linear.
Yes, you're right.
It seems to be basically non-linear to start with. It seems to be difficult to achieve a complete solution of a problem by just doing one forward integration followed by one backward integration. The idea is since the problem is linear anyway, a number of iterations are necessary. But,
I mean, I can see how you get back to a better background, and then of course you have a more accurate linearization around a better evolving scheme.
Yes.
Is there any understanding that that kind of iteration will converge?
No, mean, by, in this case, or, in this case, I don't know.
Yes, so I don't know.
What is that to say, but I can say that, for instance, at a number of places that ECM and value add, they use what they call the incremental approach, which maybe I go to the
Yes, yes. Thank you.
whiteboard. Say that it's important. Just to explain.
Yes, yes, yes.
They have a nonlinear model. NKST. And what they do, and this has the tangent linear, like the tangent linear model and adjoint model associated with it. And what they do, they start from this is the assimilation period. They start from an initial estimate at this time, and they have an objective function to minimize. They run the model, the full model, from that. And then the observations. And they consider the objective function. But in the objective function, they consider that a small perturbation from a state will not evolve in time according to the full tangent linear model to which an adjoint model is associated, with which an adjoint model is associated. But they say we are going to simplify the temporal evolution of a small perturbation in order to make computation easier and more economical. And so they will decide. There are many aspects, for instance, anything which has to do with condensation or evaporation will be ignored when one considers the temporal evolution of a small perturbation. And this leads to a new minimization problem, in which in particular they can also reduce the size of the problem by saying, this is what we do, by saying, we ignore small scales of motion. We do this minimization at a spatial resolution, which is coarser than the spatial resolution of the whole model. So they have a completely simplified minimization problem, which they solve, and they get a new solution, which has solved this minimization problem. And then, where we start from here, well, they get a new initial state, we run the complete model for the new initial state, and we do the same thing. So what we have a system of inner loops and outer loops, a number of minimizations, of difference and minimization problems. This works, but there is no proof. There is no proof, no mathematical proof. The convergence is not ensured. So it's purely a heuristic and empirical. It's very, from point of view of practical engineering, it's very reasonable. There is absolutely no guarantee that it will work. It works in practice. And it's called the incremental approach. So, in a sense, is not what you do similar? You have a reduced space somewhere.
Yes, yes.
You avoid running an adjoint model at the cost of doing computation in your reduced space.
No, the model is non-linear, so the mean is not limited. It's only the evolution of corrections. I mean, how we correct the, let's call it correction, but how we make increments, so that is not how we evolve this background error covariance is reduced, but the space is full dimensional space. So it's just like an ensemble common filter. The only difference is that ensemble common filter is here I don't make any I make assumptions, but these assumptions are based on simple concepts that are general. They are not that I don't choose wind or I don't choose whatever to make a perturbation. But these perturbations are based on a general mathematical theory, which is clear. I can say that if I look at the composition into first, 20 eigenvectors of a very complicated image, that will be very similar to what I have with a full space resolution. EOFs, no, it's enough to have 2030, and you can construct almost anything you see in the atmosphere at the synoptic scale. So that's as a linear combination of those. So that's the point. I mean, that I don't design in advance that this is the important thing, this is not, but it's the system that decides, the dynamics of the model that decide. So it's similar, for example, to singular vectors. So only the differences, major differences that actually have this inner matrix B, which weights then these perturbations. And then this weighting of perturbations require iterative solutions. So I'm not looking for the most rapidly changing perturbations, given some objectively defined criteria of norm metric. But actually, it's this background error covariances. Previous time step, they determine what is the subspace in which this can happen. So it's they limit the solution to that subspace that is already known. So if I know where the B0 and this is short, I can also do. I managed to keep more or less the whole space by doing. Okay, it's an approximation, I agree, but it's fairly, how to say, I mean, I guess, I don't know, of course this can be even made more accurate, so one can go, instead of doing the first order of approximation, go to the second order or so on. So this is kind of first order of approximation.
Okay, more questions?
Yes, we have lunch for those who are new. We have lunch downstairs in the third floor. As I said last time, lunch is 65 krona if you just drink water. Other drinks are more, also bread adds to the cost. Then we have a next talk by Shipping Young at 1:30 this afternoon. I looked at the weather forecast for this week, and it looks like the best day of the week is tomorrow. So therefore, we could have a barbecue tomorrow. I at least hope so. And in order for the barbecue to be not too late, or rather in order to enjoy the sunshine, I think we shouldn't make it too late, and perhaps a time like 3 or after 3 would be the best. People think about that.
I'm not going to come to a barbecue actually because of the whole meat thing.
But we can
But we can
at least be with it outside. We do it outside. Any other responses regarding tomorrow? 3 o'clock okay, or it's 3 o'clock too crazy? No? That's good, yeah. Good.
Any reference to outlook?
Okay, find it. Yeah.
One more thing. What would you have? We can't decide this now, perhaps, but do you have any reactions to this idea about that sort of going scheduling?
Well, you would actually be there at the in the last.
I'll be around, but I don't think I can trip.
Okay.
Just this idea of
You will sort of
merging these groups.
You will be there last week, right?
I'm not here.
Yeah, it sounds like a good idea, but I won't be here.
Yeah, okay.
Yes. You were here in the last week, right?
Next?
Me?
Yeah.
I'll leave from third.
Okay.
Yeah.
Okay. So actually,